Good evening. My name is Mark Frankel, and I am on staff here at AAAS. I direct something called the Scientific Responsibility, Human Rights, and Law program, and I want to welcome all of you to our house tonight. Before we get to this evening's business, if you will, I wanted to mention that the fourth and final program in the joint AAAS Dana Foundation series on neuroscience and society will take place right here on October 24th. That's the last in the series for this year. The title or topic of that session is The Arts and the Brain. What does your brain see and what does your brain hear? And speakers will address the neurobiology of how we respond to music and how the brain processes such things as form, symmetry, and color. There will also be a special exhibit in the AAAS Art Gallery, which is just around the corner from here. And we will have a live musical performance as well during the course of the reception. So I hope that whets your appetite and that you'll be on the lookout for the announcement with regard to that final program of the year, again, October 24th. Tonight's topic, as you know, I'm sure, is neuroenhancement, building an improved body and mind, and it's the fifth of such events in the series that started last year. We're delighted to be partnering with the Dana Foundation, which is, I'm sure many of you know, is a major supporter of grants for scientific research, for publications, and for educational programs related to neuroscience. And a video of this evening's event is going to be posted on the Dana website probably within a week or so of this evening. But we will have that information on our website as well to link to that. I now have the pleasure of inviting Ed Rover, who is Chairman and CEO of the Dana Foundation and the Dana Alliance for Brain Initiatives, to come up and offer a few words of welcome on behalf of the Foundation. Ed is a lawyer by training, but given his wide range of interests in the arts and science, he is engaged in looking at the intersection, if you will, of law, science, and arts, and many of the things that he does. I won't go through all of those. I'll simply say that with regard to tonight's session, he serves on the board of directors of the International Neuroethics Society. So, Ed, if you'll come up and project, we will we'll give you a few moments to welcome the group, and then we'll get on with our program.
Thank you, Mark. You know, it's a true privilege for us to partner with the AAAS. There are some institutions that are unique, and I say not truly unique, but just unique. And they are unique, and they do a job that nobody else does, and we're a little bit in awe of them. Thank you, Mark, for letting us work with you. It really has been tremendous. During the first decade of this century, we had an office here in Washington at the Dana Center, and we had 75 separate events there, almost all of which dealt with neuroscience. Different formats, different topics, wonderful, wonderful evening. And about a year and a half ago, we were asked whether we would reinstate for the nation's capital these great dialogues where, as our founder, David Mahoney, said, the neuroscientist came out of the lab and talked to the public, and more important, listened to the public. And I think what's really quite wonderful with what Mark and Deborah Runkle have done here is they have set up different formats, and we are constantly experimenting with those formats to make sure that you who come and others have a chance to interact with the speakers. That is not a lecture, it's actually a dialogue. We also do two other things with the AAAS as overt programs. We do lots of things informally, and one of them is a neuroscience and the law situation that has a tremendous waiting list of state and federal judges who spend 3 or 4 days together learning about what is the hope and what is the hype of neuroscience. And the other is Capitol Hill briefings, where AAAS and the Dana Foundation jointly go to the Hill and talk to staff members about what's happening. It's a great evening tonight. I think the format's a little bit different. I think this is going to be a great format. If you don't like it, let us know. If you do like it, it'd be even nicer if you'd let us know.
Thank you, Ed. I don't doubt that when you mentioned the fact that we experiment with different formats, that you were giving me the opportunity to make the claim that the fact that we don't have any sound tonight is one of those formats. But unfortunately, I can't say that. Let me explain how we will proceed this evening, if all goes well. Although the three speakers are listed in your program in alphabetical order, we're actually going to reverse them with regard to their presentations. I'm going to introduce each of the speakers individually. They'll talk for about 20-25 minutes. Following their presentation, if time permits, we'll have a couple of questions from you to them, and then we'll move on to the next speaker. The third presenter is actually a discussant. He'll give formal remarks of about 10 minutes and we'll moderate a conversation with the speakers and then open it up for you to get involved as well. Let me introduce our first speaker for the evening. He's going to be Dr. Joseph Pancrazio, who is Director of Bioengineering Program at George Mason University. You have bios of all of the speakers in your program, so I'm going to keep my intros brief. In this case, I will add that in 2004, he joined the National Institute of Neurological Disorders and Stroke at NIH, where he served as the program director for neural engineering and the neural prosthesis program. He's continued this work at George Mason University. He's going to be filling us in on that research, but also talking about some future directions that that research may go. So please join me in welcoming Dr. Joseph Pancrazio.
Well, thank you. It's a pleasure to be here. Thank you, Ed and Mark, for the invitation to be able to speak to you today. My plan is to tell you about the clinical uses of these devices, to talk about some of the emergent technologies. I want to leave you with a sense, I think the words that Ed used in terms of both hope and hype, I think are very appropriate as we think about these devices. Oftentimes, one of the problems with devices is that there's a little bit of a modern mysticism that we attach to electronic devices of all kinds. And with that, we have the opportunity to think a little bit about some of the magic that occurs when we do take advantage of those kinds of devices. So in preparing for the talk and downloading the kinds of all the slides that would be necessary, and I thought we'd talk a little bit about the science, the fiction of neural interfaces, and there's a little bit of both. We'll talk about clinical neural interfaces, and they do exist, and they are part of the standard treatment regimen for many individuals with neurological disorders. We'll talk about emergent devices and systems, including functional electrical stimulation as well as brain-machine interfaces. Part of what I want to get at and convey to you is that there really isn't a riskless neural interface or device, but these devices have the promise to restore function for individuals who have serious and significant impairments. Okay, neural interfaces from a science fiction perspective, we're familiar from everything from Luke Skywalker's robotic hand to Will Smith's more improved robotic system, where all of these have not only the capability of interfacing with the nervous system, but doing so in incredible fidelity, such that there is an incredible enhancement of a person's individual capabilities. Now, I always thought it was fascinating that Lee Majors with Bigfoot, for those of us who grew up on the $6 Million Man, was capable of deflecting objects with his single prosthetic arm, never mind the fact that his spine would have been crushed trying to pick up those incredibly heavy objects. So the truth is that the science and the fiction are, well, the science is actually stranger than the fiction. Dr. Jose Delgado's work in the 60s involved doing electrical stimulation of the caudate nucleus, a region of the brain that oftentimes with electrical excitation can induce what looks like fear in animals. And he did a rather heroic set of experiments and demonstrations. There's probably a bit of showmanship here, where he engaged he climbed into the bull ring with a bull that had been implanted with his so-called transceiver, and he taunted the bull performed an aggressive stance, and with it, pushing the button, the bull reared back and moved away. And this being really putting his life on the line, demonstrating that this idea that you can use an electrical device implanted where it's delivering stimuli to the caudate nucleus, a specific region of the brain, is capable of altering the behavior of an organism. He did work with non-human primates. It was actually had a number of social implications where he had female non-human primates making the dominant male cower. And matter of fact, she just put her hand on that button and let it roll. And he hid right in a corner. So, and this during the 60s, of course, this was quite revolutionary. And his argument was to create a less cruel and happier and a better man. These arguments very much fell short, but certainly it did induce all sorts of interesting fiction. Michael Crichton was a student in one of Delgados' collaborators' laboratories, and that created what became the novel The Terminal Man, which follows the trajectory of several of Michael Crichton's books. Matter of fact, I read it in the 70s, was inspired by it. But it is, of course, his discussions of nanotechnology and other kinds of how technology run awry. Of course, the person who suffers a traumatic brain injury resulting in epilepsy and then receive brain implants to deliver stimuli eventually goes on a murderous rampage. So again, depicting that these are technologies that certainly invoke a lot of fear, attention, and concern. But the reality is we have clinical interfaces, many of which are stimulating in nature, not unlike the one that Michael Crichton described. And these neural interfaces are, and many of us know people in our communities or have seen individuals who have cochlear prostheses that bypass damaged hair cells to restore function and the perception of sound by delivering patterned electrical stimuli to the auditory nerve. Actually, this is one of the great success stories of the NIH and public support of doing directed top-down research to solve engineering problems when the proof of concept and the science was there to support it. And it resulted in these clinically useful devices that even help in pediatric conditions. So also what came rather rapidly from the perspective of the development of biomedical technologies was the advent of deep brain stimulation for the treatment of Parkinson's disease. Where this device, where you're essentially targeting a structure that's about the size of a raisin inside someone's brain and delivering electrical stimuli on what essentially is an always or constant delivery of stimuli. So this is an always-on therapy where it's being delivered to very specific sites in the brain. Now, with deep brain stimulation, all of this became possible with the development of excellent medical imaging. Without it, we had no chance to localize the regions of the brain that are actually that are ideally targeted for this particular surgery. Still, how it exactly works is not understood. So here's an example of a patient where what is remarkable is that once you turn the stimulator on, the effects are immediately prominent. You can see in this instance, the patient this is with the stimulator off. It's received bilateral implants. The size of the electrodes about on the order of a ½ millimeter. So the next time you go over to your car antenna, or the old car antennas, look at the very end. That's about the same at the very edge or end. You'll see a wire part of the antenna. It's about ½ millimeter diameter. So imagine something like that projecting into the brain. Very flexible. But with it, you can see the situation when the stimulator is off. Immediately after activating the stimulator, you can see that he's capable of walking. Really, the cane is it's there for decoration at this point. No longer freezing, and his coordination and balance is excellent. So, let's talk about some examples of emergent neurostimulation systems. This ability to deliver current, deliver stimulation to very directed places. Retinal prosthetics have recently becoming a clinical reality. With the development of what's called the Argus tube. It was recently approved under a humanitarian device exemption for retinitis pigmentosa. This is a disorder that involves the loss of rods and cones, which are located on the back end of the retina. Light passes through the tissue and then impacts the rods and cones. And these are the transducers for light to become electrical potentials and signals that, for all intents and purposes, propagate connectivity-wise back through in the direction of the incident light to regions or cell types that are called retinal ganglion cells. And these then project to the optic nerve. This is a very convenient architecture for those of us interested in developing microelectrode arrays, because then we can think about placing, under this condition, we can place a microelectrode array that provides stimulation right on the retinal ganglion cells. Now, the issue is, how do you know what kind of signals to present? And it's not a simple pixel-to-pixel relationship. So there's a lot of processing that goes on even in this retinal tissue, and I think that's still an area of active research. Right now, this is a very low-resolution grid. Still, individuals are capable of resolving of doorways, and sometimes they're capable, it aids in the perception of the visual space. Very exciting, it actually has CMS approval. For those of you who are familiar with the regulatory process, you need not only FDA approval, but you also need a way to reimburse for a medical device, and that has been a tremendous achievement. Functional electrical stimulation, one of my favorites. It is a terrific way of restoring function in a paralyzed limb for someone who's suffered traumatic injury, especially spinal cord injury or stroke. There is some evidence for that as well. And with it, what it does is it bypasses regions that have been damaged and provides electrical stimulation in a functional, patterned way to restore what we'll call the ability to perform an activity of daily living. What are those activities of daily living? Well, grooming ourselves, being able to feed ourselves, things that you and I, we take for granted. These are the things that people who have implanted with these systems that provide targeted stimulation to muscles important for formation of grasp or arm and hand extension are capable of doing. These systems are extremely robust and reliable. The axis here is years, and we're looking at a difference between 100 and 99% in terms of electrode stability. So once these electrodes are in place, they're capable of delivering stimuli in a very consistent long-term manner. You can see this is the system actually takes advantage in this instance of a joystick, so that for some of these patients, especially what are called the cervical 5 and 6 region, they're capable of moving the shoulder, they just can't do this. So with it, the idea is having a joystick, and you can actuate or activate the stimulator such that it provides the stimuli. So one can then do this and then form the grasp that's necessary to pick up a fork, sometimes grasp a pencil, or shake a hand. Okay. So now, when we think about neurostimulation, there are three most important words, and they're familiar to you all. It's all about location, location, location. The whole geography is, and really, the clinical opportunity is parceled out in terms of what region of the nervous system, or in the periphery, and also, but using largely similar technology, similar stimulating systems. Even their package, the packaging even looks a lot like what you do for a cardiac pacemaker because of the history. And with it, there are a series of FDA-approved devices and indications. They range from the movement disorders like Parkinson's, dystonia, essential tremor, but also extending to depression now, with epilepsy is also one of the indications, and obsessive-compulsive behavior. This is a joke. It's good. So with it, we also have vagal nerve stimulation. Vagal nerve stimulation is something that, for many of us who are in the field, we think of it a little bit as snake oil, because vagal nerve stimulation has potential utility not only in depression and epilepsy, but also immune system function. What it really means is that we have to understand more about the biology and understand how to do targeted stimulation so that this very busy information, neurophysiologic information highway, we can tap into it and do so in an engineering or systematic way. There are all sorts of other kind of emerging applications. I want to draw your attention, though, to the number of implants so you get a sense of the scale of how many of these devices worldwide. Spinal cord stimulation is by far the leader. Why? Chronic pain. These spinal cord stimulation implants, these are estimates, these are up-to-date estimates of, over 250,000 worldwide. Parkinson's lagging, sacral nerve stimulation for urinary incontinence. So you can think about this as Parkinson's, urinary incontinence, pain, conditions which most often end up or most prominent in as we age. Okay? And what are we doing as a population? We're aging. The trajectory, I think, is that we're going to see more and more devices, more and more opportunities for these devices to make inroads, not only in the currently FDA-approved space, but the emerging and the future space where we don't have any therapies. Alzheimer's, for example. Can these devices actually have an impact under those conditions? Bulimia, tinnitus, traumatic brain injury. Consequently, it's big business. on the order of $2.5 to billion last year. There are a number of players in that market. Some of the companies I've listed vary in size and space. Some are working like Second Sight, or more of an emergent company, I would say, although it's been around. But they've been selling the idea. Now they're in a position to sell the devices. Medtronic has been around. They're the Microsoft of if I would pick one, of this particular industry. They have the lion's share, I believe, of the resources that have gone into and demonstrated this kind of leadership in this particular technology sector. When it comes to enhancement, I think that I go to the Dalai Lama. Okay, so during a lecture at the Society for Neuroscience, he made a very interesting statement. I'll read it to you so I can get the full impact. If it was possible to become free of negative emotions by a riskless implementation of an electrode without impairing intelligence and the critical mind, I would be the first patient. I think a lot of us would do this. If we had something that could truly enhance our state of mind without risk, why not? Okay, but so what are the risks? Well, for deep brain stimulation, again, which involves running an electrode that's about 0.5 millimeter in diameter, the risks are infection, like it is for any biomedical device. But in this case, a knee replacement, you can have an infection. It can be an issue. Infection in the brain, potential lesions, the risk is not trivial by any stretch of the imagination. Stroke due to bleeding. Well, you look at this picture, I don't see very many. Where are you going to get the bleeding? It's like a bunch of neurons. That's what we have in the brain, right? What do you mean blood vessels? There they are. Okay, so this is a vascularized representation, so you can see that. And one might look, when you look at this network, this dense network of vessels, you might ask, is the brain tissue there to support the vessels, or the vessels there to support the brain? I think that the incredible number, and I think what it should tell you is that the tight relationship, very close relationship between the vasculature of the brain and the tissue that ostensibly it serves. Now, also the brain moves. It moves a lot. You put a device in there. You have a device which doesn't move or may move very little. Does it move with the brain or not? These have differences. Think about putting a fork inside Jell-O. I think the Jell-O loses over time. And these have differences in what we call stiffness or modulus of elasticity. Nevertheless, there are ways of making recordings for the brain. We've talked about neurostimulation. We can put input, we can drive input into the brain. Much like the science fiction of Neo being able to interact with in the Matrix, this idea of the high fidelity bidirectional interface, well, we can stimulate, no question about it. Can we record? Well, there are several approaches for doing recordings, and they depend on really the scale and depth of difference or distance from the signal generating tissue within the brain. The one that everyone is familiar with is the EEG, electroencephalography. It's oftentimes used to localize seizure foci. It's something that can be used to register brain state, the idea of looking at EEGs and determining whether someone is relaxed, whether or not someone is focused. Can fall right out of microvolt level resolution of signals within from the surface of the scalp. So intracortical arrays, what I'll spend some time talking about, allow us to get as close as we can now to the recording of individual neurons within the brain. And these are oftentimes very packed or dense arrays, and you can see a picture of what looks like a bed of nails, and it's been described as such, that would essentially penetrate this pin cushion that we call the brain. Now, it looks awful, it really does. It's noteworthy to say this is on the order of 2 millimeters on dimension on each side. It can have electrodes that could span anywhere, also on the order of millimeters in length. And when you look at it up close, it doesn't look nearly, with high resolution, it looks awful, but it's not nearly as foreboding, especially for a neurosurgeon who's used, in some instances, removing large sections of brain in individuals who have no other choice, or experiencing epilepsy have no other choice but surgical resection. Okay, how do these vary? Well, clearly, scalp electrodes, from a safety perspective, is extremely safe. Bandwidth, not so much. Inversely, we tend to think of intracortical arrays as being more risky or having more potential deleterious interactions with brain tissue, whereas you have a chance to actually record activity from single cells or single signal generators, the neurons within the brain. I'm sweeping very quickly past some wonderful basic science that was federally funded that allowed us to understand how neuronal signal firing, so these electrical events that we can record within neurons within a region of the brain called the motor cortex, can be interpreted as intended direction and movement of one's upper extremity. Okay? It's wonderful science that led the way, all basic science that led the way for creating the opportunity for these real-time control, in this case of a two-dimensional cursor on a computer screen. So recording, you can imagine at the tip of these electrodes, or at the tips of this bed of nails, we have recording sites, and with that, we can record the information content that comes from these all-or-nothing events called action potentials that we resolve, decode, look at the frequency, and from that, we determine what direction the person is intending to drive their limb. Okay. So this work is over 10 years old now, and it's been really amazing. And one of the recent developments is some work that it's not just a two-dimensional screen now, a communication device, really. You can drive Outlook or something like that. Now, you have a chance to actually drive a prosthetic or robotic arm in 3 dimensions. So the decoding, the ability to determine one's intent to move and even grasp orientation, it is in information content that can be pulled from the premotor cortex and the motor cortex of the brain. Okay. Very exciting work. Now, so great, we've got bidirectionality. Let's bring Neo on. It's time to plug into the matrix. Let's go. Well, let's back up a little bit. So from a stimulation standpoint, without a doubt, what stimulation does is it allows you to provide a therapy to a very targeted pathogenic region. I've heard it described with certain pharmacological interventions that it's a little bit like the whole process of trying to treat the brain and with pharmacology is a little bit like pouring gasoline all over your car and hoping some of the gasoline goes into your gas tank. Okay? So what you're doing is drenching the brain and drenching your physiology in a compound and hoping you get enough there. And of course, blood-brain barrier, you've got issues there. So anyhow, this idea of being able to derive therapy to a very specific location is very, very attractive. And with it, though, what are we talking about? We're talking about volts. We're talking about modulating the activity of regions that are not on the order of single neurons, but they're a fairly large area, a fairly large region, and it's in the order of hundreds of microns to millimeters. Now, there's some recent exciting data that says that, well, if you're able to insert a particular light-sensitive molecule, you can actually then drive individual neurons. You can do it with light because this particular protein is something that responds. It changes the electrical activity of the cells. And since it's a light sensitive, you could actually use this approach to modulate neural activity with the spatial temporal resolution that we have of light. Very exciting. It's really swept over the neuroscience field. We're probably going to learn more about neuronal networks and the role of and pathways with this particular approach. Does it become a clinical intervention? I don't know. It's something that involves gene therapy. Uh-oh. Okay, so now the reality is, from a recording standpoint, here's where we are. We have to be within 100 microns or so of a particular signal generator to see a site. We're dealing with microvolts. We're not measuring what endogenously would be a 100 millivolt signal that's part of the high fidelity signal transmission that goes on in the nervous system, but instead it's microvolts. We're measuring extracellular action potentials. These are shadows of the action potentials that are part of the ordinary information processing in the nervous system. Also, we're talking about 40, maybe 100 neurons out of what is 85 billion that exist in the brain. Now, okay, so fine. Let's focus on the motor cortex. Okay, maybe 100 million. Okay, so still we have a fraction of the cells that are actually involved in making and performing the kinds of sophisticated movements like this. Okay? Now, with that, we also have some other issues. One has to do with the reliability of these devices. And the observation is, and this has been well known in the field, these array recordings fail over a period of time that could range, depending on technique and the laboratory and the type of array, anywhere between 6 months to 2 years. Sometimes 3 years. Now, some clinical data that's and some of this is animal data from healthy animals. Some of there's some human data that shows that you can still make some recordings over time. But the general idea is that we have effects of the brain on the device. Okay? So the brain will eat the device, and the device eats a little bit of the brain as well. So there are inflammatory responses in tissue with these particular devices, and this inflammation, according to the dogma at least, is that you'll see the presence of, and it's documented by the expression of, in local vicinity of the electrode, of inflammatory cells like microglia that we're showing in green. You're looking at a cross-section of a rat brain after an electrode has been in place, so you can see the hole in the center where the activated astrocytes are located. So they're surrounding the site, and with it, and I'm not showing you that particular image, but there's a loss of at least neuron signal generators proximal to the electrode recording sites. Okay? So with that, you know, with some of the work, and I'm only going to show 2 slides from our own lab, we're actually very interested in looking at novel materials. Many of these are made with the same kind of machinery, thank you, the same kind of materials that you would find in the silicon device manufacturing area. So what the gadgets that are in your iPhones, all the transistors, all this kind of fabrication technology, you know, silicon oxide, these kinds of materials, these are classically used for developing these very precise and almost ornate structures that we use for implanting in the brain. Silicon oxide may not be that great. Depending on who you talk to, especially in the material science domain, and we work with material, as you can see, we work with material scientists. We perform in vitro testing, which is consistent with the regulatory considerations for devices and materials. We also then take some of these devices, we put them into tissue, and we characterize the cell types, and we do that through immunohistochemistry. It allows us to see whether or not there are neurons proximal to the device or this particular material, or whether or not there are these hallmark features of inflammatory cascade. Likewise, we do the electrophysiology. Notice, do the devices work? So I'm going to show you just one data slide or one image, representative image, for some recent work that we're doing with something. It's a material that's more diamond-like than anything else. And if you look at the uncoated side here, what you can see is a lot of green cells, and these are consistent with the inflammatory response that you would see from an implanted probe. And you can see that, you can get a sense of this, and there's ways to quantify this as a function of radial distance by measuring intensity, and we do that regularly. But you can see here there's not many red cells being neurons. This is after a month of our control probe, which is the classic silicon dioxide coated system. Now, when we have something that looks more like a diamond-like coating, a lot more red cells, a lot more neurons present. And so it's very exciting for us because it suggests there may be a material component to the tissue response, and we might be able to improve the robustness of these devices. Are we going to make them so right now, right off the bat, are they going to be immediately useful for the lifetime of a patient? Probably not. But I would argue that the incremental improvements that you all have been the beneficiary of if you drove here, you had steel-belted radials or you had other kinds of tires. And basically what happened was that they're not conceptually different from the inner tube tires that Henry Ford put on the Model A. The fact, conceptually they're not, but from a material science and robustness and reliability standpoint, they're infinitely better. And they were made by incremental improvements, especially when we understand the nature of the interface of the material and its environment, as we were trying to understand with these materials that we're using for brain implantation. So to wrap up, here's what we've talked about. We talked about neural interfaces with respect to the science and the fiction. Told you a little story about Jose Delgado and really a stranger, where truth was stranger than fiction, I think, in many instances. Neural stimulation devices, they are a reality, a clinical reality for a large number of individuals who are living with disability. They are the therapy of last resort. It does involve brain surgery. It does have risk. But in these instances, the risk and benefits, the benefits of these particular interventions are really, really important and truly they're life restoring for many individuals. Now, we talk about neural recording devices and some of the scale limitations, how few of these kinds of things that we can actually record from. I gave you an example of these promising materials. So the hype, the hope, really what it comes down to is risk-benefit. For individuals who are suffering from locked-in syndrome, like some of the cases that we have now, these devices truly have the opportunity to have them live more full and complete lives. And I think there's every reason to be advancing this work for those individuals. Now, I have to show I'm under requirements from NSA, who sweeps in and makes sure that I mention DARPA, our sponsor, and also the people who do the work. And I'm really very, very fortunate at George Mason, which is an expanding campus here located out near Fairfax, for being able to do this. But I want to leave you with one closing thought. It's very often that we think about examples of science fiction leading to the next really being prescient for where the direction of science and direction of reality, where we are going technologically. And it's easy to cherry pick those. We can look back and think about Jules Verne's prediction of the travel to the moon. He wrote the book, incidentally, about something very, very different than moon travel. Moon travel is off to the side, really. Now, if all that were the case, I would have flown here in my jetpack, okay? So I didn't do that. The fact that we can do something doesn't necessarily mean it's inevitable. The risk-benefit has to be there. So I'll conclude. Thank you very much.
Thank you very much. Our next speaker is Ramez Nam, a computer scientist by training and a futurist. He's addressed the issues on tonight's agenda in both fiction and nonfiction, and was recipient of the 2005 H.G. Wells Award in Nonfiction for his book, which I think reflects a lot of what we might hear from him today, More Than Human, Embracing the Promise of Biological Enhancement. But before he comes up here, there is one ground rule that I have to tell you about. You'll note that in his bio in the program that he spent 13 years at Microsoft, where he worked on the company's email program and web browser. For those of you who have had, how shall I put this, a not very satisfactory experience with those Microsoft products, tonight is not the night to exercise any of your grievances. So with that in hand, please join me in welcoming Dr. Nam.
Thank you. Thank you very much, Mark, for that caveat. I'm not available for tech support tonight, though you can take my card. And thank you, Bethany, for setting up the slides. I'm honored to be here. I'm a member of AAAS. I've been reading Science magazine for a long time. That actually led to me writing my first book. I can tell you that story at the reception. And I've been reading stuff from the Dana Foundation for quite a long time as well, more than a decade. So it's a great honor for me to be here. As Mark said, I'm a computer scientist. My significant other, who has her PhD in pathobiology, is quick to inform me that working with computers does not actually make me a scientist. But I have great admiration for science and those who practice it. And that's informed my career, where in addition to working on computers, I've written now 4 books, all of them about science. 2 of them being nonfiction, that one, More Than Human, Embracing the Promise of Biological Enhancement, really addressing the technical possibilities and the ethics. And more recently, I've written 2 science fiction novels that are sort of near-future neuroscience thrillers. I think the first one, Nexus, is maybe the first science fiction novel heavily set at an international neuroscience conference that I know of. And they're really on the topics that Joseph was just talking about, which is a future version of an actually high bandwidth, safe to use brain-computer interface, if you will, that it goes into your mind, crosses the blood-brain barrier, does not require surgery, and networks multiple minds together, allowing thoughts, sensations, emotions, ideas to pass from one person to another, or perhaps from many people to many people. And then the novels get into not just the technology, but what are the implications of this? Should the technology be legal or should it be illegal? Who should have the control over this sort of technology? What happens to your civil liberties in such a scenario? In between gunfights and Buddhist monks and the neuroscience conference and stealth submarines and whatnot. Now, you're all familiar with these ideas, of course, because you've seen them before. If you're familiar with American philosophy, you know the words of the great American philosopher Keanu Reeves, who said, "I know Kung Fu." And I trust that all of you are, and of course it's already been referenced. But it's actually something that's penetrated modern society in other ways. Sergey Brin, one of the co-founders of Google, has been quoted to say, "We want Google to be the third half of your brain." So notwithstanding some arithmetic issues there, it leads to the possibility of the bumper sticker that says, "My other brain is a data center." Larry Page has said similar things. So what I usually, when I talk about this topic, I tell people what I want to tell you is this technology is actually being developed, and we've already heard some of that. And as you've heard, the primary motivation is medicine. That is what's driving it. So let me give you my own little guided tour, that hopefully it won't overlap too much. The origin of a lot of this technology, or the first real medical application, notwithstanding the work of Jose Delgado, who was extremely, extremely creepy, was and Robert Heath, his collaborator, perhaps even more creepy, and we can talk a little bit more about that at the end, was this invention. William House, a physician, was the first creator of this, the cochlear implant, which looks a lot like a hearing aid, right? But hearing aids work by picking up sound, which is vibration in the air, cleaning that sound up, processing the signals to get rid of extraneous sounds that are not speech, and then rebroadcasting just the speech signals primarily louder and cleaned up into the ear, where they, as vibrations, are picked up by the hair cells in the inner ear, which then vibrate, and that triggers the nerves in the inner ear to then send signals to the brain. But if you have no inner ear hair cells left, you have sensory neural deafness, and no amount of sound or vibration in the air can be turned into perception of sound by your brain. So while the cochlear implant looks similar, it functions in a fundamentally different way. It picks up sound from the atmosphere, D, that little microphone. It processes it, C, but then what it does is it doesn't send in more sound. Instead, it sends in electrical impulses directly to the nerves of the auditory nerve bundle, which go directly into the brain. So this is the first, at least clinically relevant, demonstration of sending digital input of data, of auditory perception, into the human brain. And it is life-changing. It has changed the lives of many people, like this 4-year-old girl hearing for the first time, or this 6-month-old boy able to hear for the first time.
And he's back on again. See how he turns?
Hi, Jonathan.
So you can imagine that this person's life, this little boy's life, will be forever changed, right? And now there are about 200,000 people worldwide that have cochlear implants, about half of them actually here in the United States. So whatever the enhancement possibilities of this technology, for good or ill, the grounding of it and the overwhelming majority of the funding for it and the people working on it is medical. It is people out there working to solve the disabilities and disadvantages of people who have some clear problem and doing very, very heartwarming things. And if you want, by the way, go on YouTube and search for cochlear implant, and you will find hundreds and hundreds of videos of seeing people for the first time being able to hear, ranging from this little boy, who I think is now about 3 years old and doing quite well, to I think a 27-year-old woman is the oldest that I've found. And amazingly, it still produces some functionality even when you first get it implanted at that age. Now, hearing is one sense that's very important to us. What is the sense that you would most miss if you lost it? Sight. That is what most people say. You heard about the Argus II, the retinal implant, but there's actually older work than that. This man appeared on the cover of Wired magazine about a decade ago. His name is Jens Naumann. He's 39 years old in this picture. At age 18, he worked on a railroad. He had his sight then. When he was working with a pick, picking at some rocks, slamming it in, he accidentally hit some metal, and a sliver of metal came up, flew up, and destroyed one of his eyes. He was an outdoorsman, didn't want to compromise on his outdoorsy, adventurous lifestyle. The next year, driving his snowmobile through the Canadian snows, he had a freak accident, and part of the clutch was destroyed, flew up, and hit his other eye, rendering him blind in both eyes. Okay. He was blind for 20 years until an unorthodox doctor working outside of the establishment named William Dobell did a surgery where he fitted Jens with this CCD camera, basically the same sort of camera you have in your phone, digital camera, except 10 years old, so much worse, which captures images, sends them on that wire to a digital processor, a small computer that at that time was this big, now would be about the size of a quarter, which then processes them, translates them to a different format, if you will, and sent them up to a jack in the back of Jens's head, which goes into V1, the primary visual cortex. Now, there are 256 electrodes in Jens's implant, 256 wires in this bundle, if you will. And the primary visual cortex has actually billions of neurons. So you wouldn't think this could produce very much vision. You wouldn't think this would work. There's a very large mismatch between the amount of data going in and the amount of information processing that happens in the brain. But it produces what they called limited mobility vision. So what does that mean? Well, see for yourself.
was able to very carefully dry and look from my left side to my right side, making sure I was between the row of trees on the right and the building on the left. And when I got near any obstruction in the front, I would see that there was an obstruction. I would also see the lack of obstructions. And then when I backed up, I would be able to inspect for instructions there. It was really a nice feeling.
It was really a nice feeling. So I have to speak up. I think the mic's on. It was really a nice feeling, is what Jens said. So that's a blind man driving a Mustang convertible. Now, Jens's vision, he no longer has a system. He actually wrote a self-published book about his experience, which is worth checking out. Jens's vision when he had the system was terrible. It was atrocious. But it was a quantum step up from zero vision. And it was, to me, the most important thing as a futurist and a science fiction writer was that it was a proof of principle that it is actually possible to input this sort of information, vision, into the human brain directly. Now, this sort of approach, the cortical approach, has been mostly orphaned. DeBell, the physician that did this, himself passed away years ago. Now, the retinal approach that was just approved in the US last December and now got funding approval in August is the way that's going on. But that, of course, runs into some problems if someone's retina has been actually completely destroyed. And so the cortical approach is lying in the wings and will probably come back itself at some point down the road. Now, those are both examples, proof of concepts, I would say, of data being sent into the brain. But I'm talking about networked minds, both ways. So we're not getting data out of the brain. Well, we have done that as well. You saw an example of this. Here's the first example that I know of. This is a neuroscientist in Atlanta named Phil Kennedy. He also writes science fiction himself. And his first patient of this sort, a fellow named Johnny Ray. Johnny Ray was a Vietnam vet, a drywall contractor, 53 years old, plays blues guitar on the weekends. One day, on the phone with his daughter, he had a massive stroke, just keeled over. He woke up in the VA hospital, paralyzed from the neck down. To save his life, they'd had to do an emergency tracheotomy. So he was a locked-in patient. He could not speak. He could not move any of his extremities. His only way to communicate was to blink. Kennedy had done work in primates demonstrating that he could implant electrodes into the motor cortex and train the primates to move a cursor around on a screen. So he applied to the FDA, got permission to do the first surgery of this sort in a human. The FDA had some conditions because, as you heard, infection is a serious risk. So they wanted the system to be wireless. They wanted the skull to be sealed back up. So Kennedy and his surgeon collaborators implanted a wireless system, a single electrode in a glass cone with neural growth factors that would encourage neurons to grow into it, that then communicated wirelessly with equipment worn on Johnny Ray's head and also received its power that way. And again, 100 billion neurons, let's say, in the human brain, one electrode, huge mismatch. But that was enough data to allow him to use an on-screen keyboard and type out messages. And the brain is very, very plastic. At first, it was a very, very arduous process. They actually used an fMRI at first to find out where to implant the electrode. They looked for his right hand. They said, Johnny Ray, think about your right hand. Think about moving it. When he was in the fMRI, found the hot spot in his brain. They used that as the spot to implant the electrode. And so for months, Johnny Ray had to think about his right hand when thinking about moving the electrode. Towards the end, because Johnny Ray also eventually passed away, as many locked-in patients do, towards the end they asked him, Johnny, what does it feel like when you use the system? And Johnny Ray typed out N-O-T-H-I-N-G. It feels like nothing. He had internalized the concept of this system as just another part of his body, in the same way that when you make a left turn with your car, you're probably not thinking about the steering wheel very much anymore. You're mostly just thinking about moving the car. And this work has progressed as well.
You're watching the most advanced brain-machine interface in action. Kathy Hutchinson is paralyzed and unable to speak, but just by thinking, she's able to control the movements of this robotic arm and drink her morning coffee. She's part of a pioneering study run by...
And you'll notice that motivation is very important. So that coffee, I think in the picture you saw before, it was a piece of chocolate. So I think that's very, very helpful. And I have to apologize, by the way, I do read science. I don't actually get Nature, but this is just the video that I found. They're friends. We've also gotten video out of the brain. This is a non-invasive system using fMRI. It's a very interesting system where they put people in an fMRI and they had the patient stare at a video on the left, and the computer system was trained on a library of short video clips. And then looking at the fMRI scan of the patient's visual cortex, it had to pick a video frame or a short video clip that matched up best to what the patient was looking at. I'm only going to show you one frame instead of the whole video to save time. You can see it's not very good. Outside of the brain, a non-invasive scanner has lower bandwidth, but it can kind of tell what's going on. And in fact, just this past week, there was a paper that came out, it might have even been in Science, saying that with just improvements to the algorithms, they now can, with an fMRI, determine what letter of the alphabet you are staring at, if you stare at it for long enough. So they can't tell what you're reading or anything like that. It doesn't have the temporal resolution for that, among other things. But it's getting better and better at being able to get some degree of data out of the human mind. Now, all of that has been about sensory data and motor control. But what makes us human is much more than that. We have this set of higher functions. And there have been interesting advances on that front. What film is this from? Memento, very good. In Memento, Guy Pearce plays the actor Lenny. Lenny has no ability to form long-term memories, which is rather an extreme case, but quite a large number of people in the US and the world struggle with memory problems and even long-term memory formation like him when they have traumatic brain injuries, and with memory in particular when they have damage to part of their brain called the hippocampus. So a group at USC, led by Thomas Berger, has been working on something that they call a hippocampal prosthesis that can substitute for damage to the part of the brain called the hippocampus. So they did this experiment where they took a rat, the rat had a sort of a temporary lesion, if you will, to part of its hippocampus that impaired its ability to form new memories. They could see that it couldn't learn maze properly. And then they put in essentially a hippocampal bypass, these two arrays of electrodes that shunted to this chip is actually sitting outside the brain. And they wanted to see, could they restore the rat's ability to form new memories? And the answer was yes, they could. But even more interestingly, they could enhance the rat's ability to learn new things in a couple of ways. One, they could just improve its ability to form these new memories. Two, they could very selectively record sessions of memory formation and then replay those to refresh memories later on. So they could have a rat run a maze once, and then weeks later, which is a rather long time for a rat, refresh that single memory trace, and the rat would have an abnormally good memory of that maze, much better than it should have, having only run it once weeks earlier. So this is, I think, interesting and provocative. I think quite a few of us could see uses for an enhanced ability to form recalls in our own lives. Another study on primates did something that I found quite interesting. So this study implanted a chip in the frontal cortex, the seat of the highest, most executive function in primates and specifically in humans. And then these primates were trained in essentially a primate IQ test called a pick and match test that involves matching up colors and shapes and locations of various objects on a screen. Then the primates, after learning the test and being scored, had their functionality, their performance on this test impaired by large doses of cocaine. So they may have thought their scores went up, but in fact they went down. Now, the chip had been watching as they performed on this test, and the chip was given extra data. It was told when they got answers right and when they got answers wrong. And it was observing the behavior in the frontal cortex during these sessions and trying to differentiate between these two behaviors. Then the chip was switched into an active mode, where it was given the ability to intercede when it saw a pattern of firing that it expected to be a wrong answer. And they wanted to see, could this repair the damage that was going on? Could this rescue performance on the test? And it did, and better. They could actually get scores above the norm, above the ordinary group in these monkeys with the addition of this frontal cortex chip, which of course leads to the planet of the cyborg apes. Probably not, but it is provocative that this is a very, very, very narrow test. I don't want to overstate this. This is not general intelligence, but in a narrow pattern matching test, we have boosted performance of a relatively close cousin of ours. Now, those are all interesting, but I titled this talk Networked Minds, and I did that for a reason. I'm giving this talk on a computer, and there was a time when computers were mostly about word processing or number crunching or spreadsheets, but they're not right now. The most common computers are these things, and they are primarily about communication. And in my opinion, the most powerful impact these technologies could have someday, and that day is probably decades and decades in the future, is by enhancing the ability of humans to communicate. And there are some suggestions that might be possible. So this is an interesting study performed at Wake Forest University. This took two primates, I think these are capuchin monkeys, in separate rooms with implants in their auditory cortices linked via BCI, a brain-computer interface. They cannot hear what each other are doing. They're soundproofing between them. But the question is, because of this auditory cortex link between the two, if a sound is played for one, can the other hear it? And the answer in the experiment is yes. The other can hear it, and the other can identify that sound. And this study, I said medical motivation is the primary driver, and it is. But this study was actually funded by DARPA, by the Advanced Battlefield Communications Program, okay, for obvious reasons. The idea here is, can you have squads of soldiers that intuitively know what the rest of their squad is doing? But you can, of course, see the humanitarian advantages, too. Another study, this was done by Miguel Nicolelis and colleagues at Duke, but Nicolelis hails from Sao Paulo. This took two rats, one in Sao Paulo, one in North Carolina. Their motor cortices are linked. The one in Sao Paulo has been trained to respond to lights and hit the right lever in a cage. The one in North Carolina has the same lights, same cage, has never been trained, but when their minds are linked, when this link is activated, the one in North Carolina starts getting the right answer well above chance, about 70% of the time. Not 100%, but 70% of the time, because of the input from the motor cortex of his peer in Sao Paulo, and that is a gimmick, by the way. Once you can link brains, you can link them across any distance that light can travel in a reasonable amount of time. But that is a provocative gimmick. And the day that my second novel came out, people I don't know yet, but I will, at the University of Washington, just a few miles from my house, did this experiment, or released this experiment. This is Professor Rao on the left, and I'm afraid I've forgotten the name of the professor on the right, at the University of Washington. They're on separate buildings at opposite ends of the campus, and they're playing a video game together, but in an odd way. Rajesh Rao can see the screen, but can't hit the button to fire. His colleague on the right can hit the button to fire, but can't see the screen. Rao is wearing an EEG that is set up to determine his intent to fire. His colleague is wearing a magnetic stimulator oriented to produce a current in the motor cortex, in the part of his motor cortex controlling his right index finger. And so together they play the game. And it's not that his colleague feels a tingle and says, oh, I should hit the button. It's that his colleague occasionally feels his finger twitch and hit the button. And they win. They can't hit the good guys. They can only shoot the bad guys. But it works out. And of course, this is now just speculation, but people have talked about, and Berger at USC, who did the hippocampal chip, has talked about what would happen if they had two rats with hippocampus chips, and they trained one to run a maze, and then bridged that information to a second hippocampal chip in a second rat that had never seen the maze. Would you have a Keanu Reeves moment or not? Probably not on the first try, but that is the sort of thing being asked. Now, challenges, I'll just whip through these. There are some. This is the first challenge. Jens, the blind fellow, that was his, on the right, is his level of vision. 256 pixels, 16 by 16. Now, the Argus 2 is closer to the bottom left. You have to get a little ways better before you would even consider having this as your vision. This is not the bionic man. This is not the $6 million man with his telephoto zoom eye that is tremendously better than your eyes. This is the other way around. Okay, so that's one. Brain surgery, you've already heard this. The risk is very, very high, and the reward, as you just saw, is very, very low. Of course, that's been said before. We used to hear no one would ever voluntarily have eye surgery. And indeed, 20 years ago, there were about 20,000 eye surgeries in the US per year, and basically none of them were voluntary. But then we invented something called the excimer laser. And now there's about 1.5 million eye surgeries per year in the US, and almost all of them are voluntary because it was a technological breakthrough. Now, I don't think there's going to be a LASIK of brain surgery next year or even next decade, but it could be one 30 or 40 or 50 years from now, bit by bit, perhaps, or small incremental changes, as they say. Another challenge is, something's wrong here. Well, I'm sorry. I'm going to have to work on my slides. Of course, a computer in your brain would never have any problems whatsoever, nor would it be infected by viruses or ads for products you don't want or malware. Okay, all of those are technical issues, but let's get to the real issues, because this is supposed to be about the ethics. There's two big issues, I think. The first is, what does it cost and who can afford it? That is honestly, for most of enhancement, when you cut right through the moralizing, when you cut through the should humans be better, when you cut through human nature, this is the majority ethical issue most of the time. And sometimes it just works out, and sometimes it doesn't. Do you remember the digital divide? We were extremely worried about that, and it was a legitimate concern. We were worried that people who were lower income in the US or worldwide would not have access to digital technology and would be left behind. Now, at that time, the price curve on these things has been phenomenal. And so now there are more people with phones in Africa than there are in the United States. So this has been a great equalizer of society, and thank goodness. But we do not yet have a guarantee that this sort of technology, if it ever develops, will go in the same direction. So that's legitimate concern number two. Number one. Legitimate concern number two was actually the one that I spend more time on in my novels, is this one. It's the question of control. If you have a technology like this, who gets to control? You've already heard about Jose Delgado. Delgado's colleague, Robert Heath, was perhaps even more creepy. Heath did experiments on humans. Patients in asylums in those days had very, very few protections. Heath did experiments with a gay man, where he hired a prostitute and attempted to use a prostitute and in neural stimulation of certain centers of his brain to try to change this patient's orientation, with no success. Delgado wrote this book, Physical Control of the Mind, where he proposed that brain-computer interfaces, or neural prosthetics, could be used to keep criminals from committing crimes again. More germanely to the present, we have questions about the NSA in the United States, or more severely, the censorship that goes on in China and Iran, for instance. Now, all of that having been said, I am an optimist. I think these are real issues. But when I look at history, the long-term trajectory of information technology, which is how I view this in a way, of new abilities for people to communicate, is actually one that is tremendously positive. From the invention of language, to the invention of writing, to the printing press, to the internet, we have seen that these new abilities for humans to communicate, which have also been enhancements of our intelligence, have done two things. One, they have increased our rate of invention. And I'm down to my last slide. Without the printing press, we would never have had the scientific revolution, the germ theory of disease, the steam engine, the light bulb. All of those rested upon the ability of scientists and engineers to learn what others had done and to communicate their ideas. But the printing press also made possible the spread of ideas, such as those of Hume and Locke, who wrote that the governed should have the right to choose who governs them. They made possible the spread of ideas that the blacks, the African American, should not be enslaved, that women should have the vote. All of these things, all of the progressive ideas that we have, that America should be free, have all been spread and accelerated by our ability to communicate. So my view is that there are very serious risks in any new information technology of over-control, but that if we manage those, it can be, and most likely will be, a potential liberator of humanity and a potential accelerator of our rate of innovation. So, thank you very much.
We're going to wait for questions until a little bit later so that we can move on. Now we're going to move to our discussant and ultimately our moderator for the rest of the evening, and he is Dr. Dauphin Chen, who is Program Director in Systems and Cognitive Neuroscience at the National Institute of Neurological Disorders and Stroke at NIH. He has a long-standing interest in bioethics, especially as it applies to neuroscience and the relationship between science and society, and it's my pleasure to turn the remainder of the program over to him. And again, remember, let's just make believe the mics work as we go forward with regard to the discussion here and the questions from the audience.
Thanks, Mark and Ed, for the opportunity to participate. Now it's hard to follow these two great speakers, and I hope I can offer some perspective as a neurophysiologist, and also try to give some information regarding neuroscience research at NIH. Now you notice that I put some parentheses on the improved, and it's not trying to say that enhancements is not possible. In fact, we are doing it already. So if you look at the NIH mission at the bottom, that we have enhanced in our mission. So NIH is not just trying to come up therapies for the sick and illness or disability, but we also intend to have ways to enhance health and lengthen life. So this is in our name. And as far as neuroscience research, we spent about $5.5 billion out of $30.9 billion in FY12 in neuroscience research. And that's been coordinated by about 15 institutes and centers across NIH to leverage resource to do cutting-edge neuroscience research. So that's a quite extensive and high priority area of research at NIH that we support across the United States. So talking about enhancement or augmentation, so if you go to NIH report, which is a database that you can search all the projects funded by NIH, you will find many projects have enhancement augmentation as one of their aims. But if you really look at it carefully, there are differences between therapeutic versus beyond therapy. And many of them are, some are absolute enhancement, others are compensatory enhancement. And we also, you can see the difference between some are just modulate or optimize within a normal range of our capabilities, or some are, beyond that range. So it's hard to find a division to decide which one is which. Often it's not that clear. And often we have a hard time to actually find, identify, or quantifiable normal range or baseline. And that's especially true for neurofunction. So for neural or cognitive function, and in terms of neuroenhancement, the question scientifically, first we need to ask, can we? But I've already laid out that if we cannot define the normal range with a very clear neurobiological basis, or define the baseline for that, and then it's very hard to say how enhancing are neuroenhancers for, especially for non-medical users. And then the other question is how cognitive is neural or cognitive enhancement? Are we talking about the real human cognition, or is it some elements of some kind of a cognitive behavior, but it's not really a cognition? Again, as I said, at a neuropsychological and a physiological basis for baseline, a normal range, it's not that clear. Now, if we do, if we are capable of enhancing, should we, and how? This is really ethical, legal, and social, has these implications. Is it desirable? And what's the goals and the consequence? And there are whole sets of issues in terms of safety, coercion, and I listed here, and you can find, we don't have time to really discuss these things, but you can find lots and lots of literatures on this topic. So the policy implication. So if we can enhance cognitive function or neural enhancement, then what we need to do? I mean, there are different opinions on it. I mean, one extreme, of course, is just say, well, the lure of these technologies for sellers and users are very high, and we should basically leave to the mercy of the market force. And the other extreme would just say you have to implement new laws and regulatory structure. A third, a middle ground kind of a proposal is trying to emphasize that a combination of multiple mechanisms is needed, including research program, leadership from relevant professionals, and also the public education. And then coupled with some careful and limited legislative actions. So the very recent study by Martha Farah at the University of Pennsylvania really questioned, for instance, the smart pills, and what their study, taking a close look at the evidence and find very little or no effect on cognitive ability, even though the pill has been used widely as a cognitive enhancer or neural enhancer. So they think that amping up motivation to work can just greatly enhance one's productivity or learning. So smart pills are really a mere motivational lift. And there are some meta-analysis on whether or not stimulants have any net positive effect on executive function or brain learning function, show very, very small effect. So basically, there's no evidence whether smart pills truly improve cognitive ability through a known neurobiological mechanism. And also, many research pointing out there is a lack of rigor in many of the studies that have been performed. There is also transparency in reporting. So these are the issues that the field needs to address before we can say with high confidence that their cognition has been enhanced. So the message I was trying to make is we simply know very, very little about how brain works and about how the neural basis of our human behavior. And it's still within this scale, it's a mystery to us. And that's not been unnoticed. And as you see that the president launched a new initiative in April, the Next Great American Project, to launch a new effort. And as the president said, there's this enormous mystery waiting to be unlocked. And this particular brain initiative will change that by giving scientists the tools they needed to get a dynamic picture of the brain in action and better understand how we think and how we learn and how we remember. And that will be transformative. So it's going to be focusing on developing innovative technologies and try to construct a dynamic picture of the brain function that integrates neuronal and circuit activity over time in a space. And then this is going to be a highly interdisciplinary effort and of an unprecedented scope. So this will be led by by NIH, but it will be participated by 3 major government agencies, DARPA, NIH, and NSF, and also have been joined by some prominent private organizations like, as I listed here. And then in addition, many industry partners have expressed interest in joining, including IT companies like Google. So the director of NIH have appointed a working group and consists of 15 scientists with expertise in different fields, and they will try to come up with goals and develop plans and recommendations, also set up milestones for keeping track of the development. There's there are a series of workshops and conferences and RFIs to seek broad input from the research community and from the public on priorities and opportunities. So this is also going to be coordinated and synergized with effort in other countries. So the focus is going to be looking at the analysis of a circuits of interacting neurons and looking at the circuit, measure the patterns of dynamic activities, and understand the resulting cognitive and behavioral capabilities. And this is going to be interdisciplinary, multi-scale, and will pose problems, not dictate solutions. So this is going to be make NIH or the community quite busy for the next few decades. So the president, when he announced this in the White House in the East Room, he did express concern over the ethical implications of this initiative, and he directed his Bioethics Commission to make sure that the research is being done in an ethical manner. And the commission started working on it right away already in August. They have already began their deliberations, the first deliberation, and there will be more deliberations in the future. And you can follow up these with more details and updates at the NIH website. So with that, I just want to say that we are excited with these opportunities and believe that this initiative has the ability to articulate the significance of the brain science and capture the public's imagination. And then we hope that this will be the seed for a long effort, an effort not only for discovering how our brain works, but also an effort for recalibrating people's expectation for the science, especially for the neuroscience. That's all I want to say, and thank you. So if I may invite our two previous speakers come and join me. And
so I thought your talk was very interesting, and I thought that there are a number of examples that you provided that I thought were very exciting. I think your analogy about as communication devices and thinking about this as an information technology is interesting. I'm also struck by the fact that I'm incredibly uncomfortable with the fact that my droid is now off as I'm sitting up here. And I think that's a measure and a testament probably for all of you and all of us, how tied we are to these amazing communication devices, this democratization of information, the Arab Spring that was Twitter-based, the fact that you can have communication in ways that is very much like what you described from a mind-to-mind way. So I think the analogy of thinking about this from an information technology is provocative, it's interesting, but also there's one element of these devices. They're incredibly disposable. Yeah. These are things that we use for a few months, we get tired of, and we throw away. The notion that we're going to have implantable devices, and I have the iBrain 1.0, and you've got 5.0. I'm wondering just where this analogy with consumer electronics, and that consumer means used and thrown away, and that's the modern world, folks. It is. How that fits into this idea of the communication space that would happen with implantable technology. The other thing that, and I'll give you a chance to ruminate there, and I also think about the idea that there are a few times now, we do turn them off. We do have these moments where we put the communication aside, and the fact that I can put this right here, I know that I'm not going to get a contact from my son, while I'm talking to my wife or whoever from work, I can put that aside. I think about Thoreau going out into the forest, being able to construct the work that he did, Jesus going on his 3-year ordeal of discovery. What does it mean for a future where we're all interconnected? Do we lose the great works of Thoreau, the inspiration and the discovery of Jesus? I'm picking that as an example. It's the one that came to mind. It's not to, I'm trying to get bring in other dimensions. I mean, so anyhow, I'm curious what you think.
Well, I think those are great questions. I think the upgrade problem is a great one, actually. One's been brought up before. Greg Stock, who's a great bioethicist also, has written about various genetics as a future frontier. He's talked about this as one reason he is skeptical that we'll ever see implants. Surgery, he uses one obstacle, but the upgrade question also. Would you ever decide to get an implant in your brain if you think that next year a better model is going to be out there and you're going to go through surgery again? So I hand-wave this in my novels by saying, oh, you can drink it, and it's nanoparticles that cross the blood-brain barrier and then self-assemble. And that is total hand-waving. I don't think that'll ever, maybe ever is a big word. I don't see any horizon for that. So I think it is a big technical question. I don't know if it's actually feasible or not. I know the Air Force actually, through DARPA, has a big program on MEG. And could MEG be something that has much better resolution than EEG and get to some non-invasive thing that's somewhat good? I kind of doubt it myself. So it's possible this will just never come to pass. If it does come to pass as something that people actually use as an enhancement, I would suggest that the way it will happen is a scenario like this. The way that it would happen, I think, that is most plausible is someone that has a disability, maybe from a traumatic brain injury or something along those lines, gets an implant where they are forced to go through the surgery or where the risk-reward profile is different because the reward is so much higher, and where the implant is sufficiently advanced or comes with sufficient other flexibility that they're able to get some benefits out of it, and then they have some advance. And we talked about the fact that distance becomes very little, a bit of an obstacle, right? The current retinal implant, it actually has photoreceptors in the back of the eye. But there's other models that were considered, and they're still being developed in labs, that don't have the photoreceptors here. They're setting a photoreceptor on a camera on the glasses that transmits information. With a cortical prosthesis, the data input can be done from anywhere. If you have that, there's no reason you can't be inputting data, video data from the web, from YouTube, from the surveillance camera on your house. So that's a sort of scenario where somebody that is handicapped could get an implant and then find that there's some aspect of it that enhances them in some way beyond and that might be the entry point to something like that in society.
It's interesting. I think that one of the big drivers for enhancement in general is cosmetic. In some ways, yes, it is about presenting information in a more clear, complete way, but it's also about getting rid of the glasses and the fact that the risk, and I think what we see it's interesting from prosthetics, especially the notion that some of the returning veterans that have received prosthetic limbs, they're asked, well, would you want your prosthetic limb to be flesh-colored and toned? He says, no, I like it being black. Okay? So this idea of ornamenting, this idea that there's a cosmesis or a cosmetic concept to some of these, quote, enhancements. I think it's sometimes, it would probably be a significant driver if we do think about technologies. We already ornament ourselves with earbuds. You know, we do that sort of thing. That's very common.
So these are very good discussion, and I think we can have this go on forever.
Forever.
I can see these two engineers are really excited by these things. So
He's a scientist, I'm an engineer.
We're
in the interest of time, and in fact, I have some very specific questions for both of you, and it's kind of common. So I see the risk, of course, there's a technology-wise, there's a risk of using these things in all kinds of consideration, but there's also a risk, as I said it at the end, a mismatch of the public's expectation of this technology and these technology really can offer. And that's a risk to the whole research enterprise. If we, this is a complicated part of our body. If we do, another 50 years of research and it will not be able to deliver, and that would be a problem. So that's I see. And now, why I say that, in fact, as a neurophysiologist, and looking at all these things, many of these things could have been done 100 years ago, or even 50 years ago. And the very reason we can't do it now is not necessarily the advancement in neuroscience, is actually contributed by your former employer.
Or material science.
Material science.
Yeah,
So
yeah.
it's because all these computer technology, IT technology allowed us to do lots of real time. That's, you see some of these interface that can be accomplished. So I try to emphasize the public's role in supporting this enterprise, but then the question is how much you really understand when we talk about these things. So I have a question direct to Joe. For today's talk, if you are going to give this talk at Mesa, as a course, what kind of a prerequisite you would ask from your student?
That's a great question.
And then you say, well, we'll give you a test on that. And then it will be a really tough test. And then what will be the prerequisite?
Well, so we do give talks very much like this. We actually have an introduction to bioengineering, and there are no prerequisites to it. We use it as a conduit to engage students in the opportunities of working at the interface between biomedicine and engineering and computation. And with that, we have a responsibility to be able to speak to students and engage them at their interest level and engage students at as many different levels as possible. I think the major point that we try to convey to the students is that there's a tremendous opportunity for making contributions to the quality of life of individuals who live with disability. And that this is a noble enterprise. It's something that's the basis of medicine. It's an opportunity now for engineers with it, and one of those opportunities being realized by real-time computation and very much in the examples that you see. But there's an opportunity to make those kinds of contributions. And I think that our job in these bioengineering 101 classes is to inspire and to get the students to be starting to ask questions of this nature. So there aren't any prerequisites necessarily for this.
This could be given without any prerequisites.
Well, I think that at this point, there would be some more. So first of all, it would be probably twice as long. And there would be examples of explaining the basis of how the information is transmitted within the nervous system, giving concrete examples of this action potential basis, what exactly that means to the frequency modulation of the nervous system. But I find that many of the students, especially that have grown up in IT and are extremely savvy, they've grown up in many instances with the knowledge and the inspiration of science fiction novels such as yours. They are thinking about these kinds of opportunities. They see the interconnectivity. They experience the interconnectivity, and they understand that we have the opportunity to be able to think and share ideas very rapidly, and this is fundamental to who we are. So, anyhow, I'm moving away from your answer.
I give you my physiologist perspective.
Okay.
Right. So if I would teach this material in a physiology program, let's say, and I would require a 400 level physiology or neuroscience to be really understand, to be really able to understand what I'm talking about and really do some meaningful tests on the material.
So that's true, but then you use analogies that are very important. You try to make concepts and ideas very. So virtually every kid who's had an ankle sprain understands what inflammation is. And this idea that the swelling, and so you use examples that kids and everyone understands. And you try to make those concepts understandable, that inflammation doesn't matter if it's your ankle or your brain, it's bad news. And with it, you have difficulty because you put something that's very, very stiff inside of a brain. It's like putting a fork in Jell-O. All the kids have been eating Jell-O since they're 4 years old. So I think that if I get up there and talk only about the cell cycles that are involved in inflammation, where I talk about microglia, macrophages, and all that nonsense. Bottom line is that it comes down to inflammatory tissue response, the idea that the body rejects these kinds of materials and devices unless we're smart enough and we can engineer them to reduce that kind of response. So I think, to your point, we have to make sure that we have a responsibility as scientists and educators to make our message understandable as much as possible. And that's really human-to-human communication and teaching and exchange of ideas.
So, the reason I want to emphasize this is about the level that I think with that level of understanding, then you can make a decision whether you want to have an implant or how DBS works. Right? And so this is the difficult part of this area of science in terms of public understanding of neuroscience and the expectation from the public versus how much technology can deliver.
Can I say one thing? And I'll
Yeah,
let you, and
please.
I'll shut up. So and I think the public understanding of science is absolutely critical. It's also being able to distinguish a stunt from scientific progress. And the example with Jens and Dobell could sell sand in the desert. He was a showman.
Yep.
He pillaged the Lions clubs and to get money to be able to do these surgeries outside the United States. And he used these pads of cortical electrodes. Jens had seizures because of the electrical stimulation that goes on. So yeah, he drove the car. It's a stunt. Okay, are people working on cortical stimuli for visual processing? Absolutely. But it's the incremental, slow nature of basic and applied science. It's not showy. It doesn't have these big flares of excitement. But it's absolutely critical to maintain the enterprise. I'm sorry, I'm done.
Oh, DeBell definitely, he did his work in Europe to avoid US regulators who would not give him permission for his work. So he was not as bad as Delgado, but he was his own sort of phenomenon.
All right, so now we open the floor for audience question. Well, Ralph is here.
So I wanted to raise the issue, our brains, I'm Ralph Nitkin. I'm also from the NIH. I'm in the area of medical rehabilitation. But I'm going to actually play the other side of the argument now. Our brains have evolved. They're really fantastic tools, and they've evolved for very specific functions. Now we're adding all this sensory input. We're adding extra information. We're adding stress. And I think we have to be a little careful about what the effect of this can do to us. I think about two quick stories. One is the story that Oliver Sacks tells about a man who had his vision restored late in life, and it was so confusing to him, it actually drove him insane. And then another analogy is, for example, in cars. We give people the ability to drive faster, much beyond their means. We give them all these distractions and iPhones and things and one way we responded is not by giving us electrode, it's actually making the car smarter and making us dumber. And so, as a rehab scientist, I'm all for restoring function, but this is augmentative, and so I'm wondering about the effect of giving people extra sensory overload, the stress effects is going to have. If we have Google glasses where we can always be on the internet day and night, think about the effects of that. So I wanted to raise the issue about what's the effect of that going to be about going over and above?
Well, I think it's an excellent question, and I think we see some of those effects already. My friend Linda Stone coined a long time ago her phrase, continuous partial attention, which depicts the situation that we're in right now already with our smartphones, even before Google Glass. And it's a common thing that multitasking, most people think that they're very effective at multitasking when almost no one really is. And so we have to learn what actually works for us. And it may be that we find out that there isn't much of an augmentative path. It could be that we try these things and find out, oh, actually, you can't do it. Or you can do it, but the toll is so high that you don't want to. But at minimum, I would say, at minimum, we're going to get two things out of this. At minimum, we're going to get restoration of function from people who have been harmed. And secondly, which neither of us have talked about today, we're going to get great insight into the actual structure and function and working of the brain and the mind. Because right now, it's such a mystery how, at the level of how do the circuits and the behavior of the firing patterns in those neural circuits actually relate to cognition and cognitive processes. And I think a lot of people in neuroscience agree, that it's going to be at the level of recording small bundles of neurons that we're going to actually start to get insight into what's going on there. So at minimum, I think we're going to get those two things. And then hopefully, and I'm optimistic that we'll get some, we'll find some ways that are augmentative as well. And then some, perhaps, that we'll find out, oh, we probably don't want to do that.
Jason Alls, Department of Defense. I was wondering if I could get the speaker's thoughts on BGI's genomic sequencing efforts to understand the genetic architecture of intelligence, particularly that of profoundly gifted people?
I have a couple thoughts.
Please go ahead, because I'm still trying to decode the
I don't know.
I'm not one of those gifted people. I'm an engineer. You have to speak very slowly to me.
I don't know about BGI specifically, but I know that the most recent work that I've seen on the genetic architecture of intelligence is that there are at least 500 genes that contribute to human variation and intelligence. The largest single gene we've ever found that contributes to human variety and intelligence contributes about 3% of the human variety that we know of. It's the COMT gene. And the alleles that are correlated with high IQ are also correlated with high incidence of schizophrenia. So I absolutely think that genetic manipulation of memory and pattern matching and so on will be possible down the road. But I think that finding that it's so spread out among so many different genes means it's going to be very complicated, and it's not going to be a purely upside sort of phenomenon, most likely.
Just a little background, I guess not a lot of people are familiar with that effort, but they've sequenced 2,000 profoundly gifted individuals, and we're expecting the results anytime in the next 6 months on this. And the upshot on it is that it looks like there's going to be a strong genetic correlation with gifted intellect.
Cool. Can't wait to see it.
Hi, my name is Lauren Milner, and I'm a AAAS Policy Fellow at the NIH. And Dr. Chen, you were talking about the kind of public expectation and education, but I was wondering if any of you had thoughts about kind of public repugnance or distaste and how that might shape the future of these technologies, with the obvious example being the Jesse Gelsinger case and gene therapy, and how that really had a huge negative impact on progress. So I guess my question is, what role do you think public distaste will play, if any, and how can we work with that, or what preventative measures can we take?
You want to take that?
I'll let him think about it for a second. And I think this is, so I think a lot of this is, these are issues that many of individuals who are working in this field regularly are concerned with, and partly because the use and reliance on non-human primates for a good amount of the work that you've seen that's led to the ability of doing this multi-electrode recording for controlling the 3D control of robotic limbs. So there is a tremendous sensitivity among the scientists about how their information is presented. And I think that from certainly those people who are sponsoring research and are involved in the research enterprise have to be sensitive to issues associated with use of non-human primates, without a doubt. So that's one example of how, and if it's not treated sensitively, we run the risk of inducing this repugnance that you refer to in the public, and far more than that. Now, as far as the kind of broader issue of that taxpayer in Nebraska, that grandmother who says, I'm just against brain chips because they're just making other kids smarter than not my kids. And I think that that's something that we have, that the opportunity to be of service of mankind, to restore function, those individuals who have lost the ability to live as complete and full lives as they deserve, and I consider it almost it's not only a moral argument, but also I would argue as part of ADA. We have a responsibility to provide access, and it's a measure of who we are as a society to do this. So I think that the focus has to be, from a science and presenting value from the scientific community about restoring the function of those who are less fortunate than we are. Now, I'll let my colleagues talk about, please add.
I think in the Jesse Gelsinger case, that's one sort of backlash against failure and risk. I think that when I hear repugnance, I think more of the backlash against IVF, cloning, and that sort of thing. And I don't see that happening in the case of neuroprosthetics nearly to the same degree that it happened around genetic and biological and reproductive technologies. There just seems to be more of an ooh-squick sort of reaction and a religious component to anything in the reproductive path and the genetic path that I don't see happening in the the neuroprosthetic path, right now at least.
Take that last question.
My name is Samar Chatterjee, Safe Foundation. I want to focus on one of the things one of you mentioned was implants. Now, is there a lot of experimentation done with implants? Because I would, and there was I think one of the gentlemen mentioned that you have to do the surgery again and again. And I'm just wondering, do we understand the neurons and whatever is in your cognitive agents enough that we could put a connection to what is implant is just a connection, and so there will be another device outside which will link either wirelessly or through a wire. And that would be a better way. That way you don't have to do the surgery again and again as technology improves and so on. So is there something of that sort? Because this not being my field, that's the question I have, is how are they approaching it?
The answer is yes. EEG actually is a way of, you don't have to get into the brain. And it's non-invasive. But of course, if you really wanted to get high band signals near the neuron, you have to be invasive. I mean, as far as the technology is concerned. Joe, if you want to add.
Well, I think that what you're getting is how. How do you go about actually providing a device? And I think that probably the most feasible way of having a device, and I think that certainly work, and you can see the field moving in this direction, isn't so much an all-in-one package. It would be, a separate set of interconnects that would, much like the deep brain stimulation device and other kinds of packaged devices, would have a tether that would run underneath the skin to some kind of central package. And that central package would, be either, would provide battery source as well as communications to an outside device or system. That's probably the most likely implementation when we get to the point of a truly fully implantable system for a human being, such that this idea. Oh, well, so there's work going on in that space. Are these clinically available? No, not by any stretch of the imagination. But there's certainly work that's going on at Brown University in developing. So the question is how to do it. What's the right orientation? I think the path that's been pursued by the implanted medical technology arena will be that path. So you can imagine that the implant will look a lot like a DBS arrangement. You have a packaging that's underneath the skin, tethered, run up to a connector that goes in with the brain. And the idea is that electrode in the brain doesn't change very often at all, much like you described. But the electronics at the back end could be updated and modified, but still it's packaged internal as a true complete implant.
Let me ask you to join me in thanking our panelists, please.